Welcome back, everybody. We've really come a long way because in this new chapter of our course, we're going to start talking about sampling distributions and eventually hypothesis testing. If we're ready to talk about hypothesis testing, that means we're ready to conduct our first inferential statistical test. So we've really learned quite a bit so far, but we still need to learn just a little bit more before we're ready for that first z-test. And specifically, we need to learn about sampling distributions. So for this chapter of the course, I'm going to break up the videos so that there are a few about sampling distributions and then a few about hypothesis testing. Let's first focus on sampling distributions. The bottom line is that when we collect research data, we collect data from groups of people, samples of people. So if we're going to use z-scores to compute probabilities, we need to be able to extend our conversation from computing probabilities of individual scores to computing probabilities of sample means. That's where we're headed in this video. Let's go ahead and get started. Let's remind ourselves first of some basic stuff that we learned previously. We learned that probability equals proportion of area. And z-scores provided that bridge between our data and computing probability. So, for example, if I wanted to figure out the probability of scoring 5 or greater in this distribution, I can simply figure out the amount of area associated with scores in that range. We learned that we could convert 5 into a z-score and then find the area in this tail. So in that regard, z-scores were great because they were allowing us to figure out how much area was represented by scores greater than or equal to 5, which allowed us to know the probability of somebody scoring greater than or equal to 5. And stated another way, a way that's more closely related to what we need to know, using that method, we were able to figure out the probability of randomly selecting from that entire distribution a score that is greater than or equal to 5. These three questions, although they're all stated slightly differently, all ask essentially the same thing. So those z-scores turned out to be incredibly useful because remember, we can convert anything that we measure to a z-score. And then once we know a z-score, we can use that handy-dandy z-table to figure out the probability of scoring in any range. The good news is that we're going to continue to use those z-scores. We just need to start using them in a more focused situation. Let me show you what I mean. As I mentioned previously, we're typically measuring groups of people. And how do we summarize information that we collect from groups of people? We compute group means. So if I'm comparing two groups, like 50 people who are treated with Prozac compared to 50 people who are treated with simply a placebo, then I'm going to be very interested in their mean scores, their mean depression scores. And in this case, it looks like the mean depression score for the people who are treated is lower than the mean depression score for the people who are not treated. We discussed previously that there are two competing explanations for those results. One explanation is that the difference we see here between these two sample means reflects a real difference that we would see between the two populations, the population of treated people compared to the population of untreated people. The other explanation is essentially the opposite, and it states that the difference we see here between these two sample means does not reflect a difference that we would see between the two populations. That explanation says there is no difference between the population of treated people and untreated people. And this difference that we see here between the two sample means is simply due to sampling error. Well, I've mentioned this before. You know where we're heading with this. We need to figure out what's the probability of finding this type of difference just due to sampling error. But to be able to do that, we need to be able to transform these sample means into z-scores, and we haven't done that yet. We have transformed individual scores, individual x values into z-scores. We have not transformed sample means into z-scores. Although the math involved won't be difficult at all, I promise you that. As we start linking z-scores to sample means, there are some new concepts that come up. And those concepts are probably going to require some time on your part to wrestle with them, to really understand them inside and out. And that's okay. You just need to give yourself some slack. You can listen to these videos, listen to them again, spend some time thinking about it, ask a question or two. But this part right here that we're going to start talking about, distributions of sample means, it's really important. It's important to make sure you can nail it. So let's get right into it because our focus is going to change a bit. from a distribution of individual scores to a distribution of sample means. Let me change the view so I can take some notes with you along the way. As we've worked with z-scores and probability to this point, everything has focused on a distribution of individual scores. And that's what this distribution on the top represents. It's just a distribution of x, a distribution of individual scores. That information is listed right there in the description, but let's list it again just to make sure we really understand it. This is a distribution of x, of individual scores. So when we look at that x-axis, we are dealing with x values, just individual scores. And of course, on our y-axis, we're dealing with frequencies, relative frequencies in this case. And of course, we were able to take any x value. For example, a score, an individual score of 110 on an IQ test. Transform it into a z-score using this formula. Figure out exactly where it is in the distribution. It might be right over there. And then answer this type of question. What's the probability of scoring 110 or greater? All we would need to do is find the area in that tail. And then we can answer questions like this. What's the probability in the entire population of randomly selecting somebody who scores 110 or greater? Well, what we need to do is extend that conversation to distributions of sample means. So although this distribution on the bottom looks similar to the distribution on the top, it represents something somewhat different. So let's label it. This is a distribution of sample means, x bar. So in this case, on that x-axis, we're not graphing individual scores anymore. Now we're graphing sample means. So let's label that x bar. The y-axis still represents frequencies, relative frequencies actually. I'm going to explain to you soon that it will be this distribution of individual scores that gives birth to this distribution of sample means. And if that distribution of individual scores gave birth to that distribution of sample means, then we can view that distribution of individual scores as the parent population. I find that analogy to be very helpful here. Think about parents and children in the human world. They often share a lot of the same qualities. They look alike, they often think alike, they often act alike. In other words, once you know something about the parent, to some extent you know something about the child. Well, once we know something about the parent population of individual scores, we also know something about this distribution of sample means. Keep in mind that we will usually assume that our data comes from a distribution that is normally distributed. Well, look at that distribution of individual scores. It is normally distributed. Look at the distribution of sample means that it created. It is normally distributed. So they share the same shape. Here's another characteristic they share in common. Look at the mean of this distribution. Assume again that we're dealing with IQ scores. Average IQ score in the human population, 100. Well, look at this distribution of sample means. What's its mean? We call it the expected mean. That's why you see a mu sub e. It's the mean that we would expect to find. And what does it equal? It equals 100. That's the same mean from the parent population. So a distribution of individual scores and a distribution of sample means that was created from that distribution of individual scores, they share the same mean. What's another important characteristic that exists when it comes to these distributions? Really, the only other characteristic that we talk about is the amount of variability that there is. Remember, the variability in a distribution of individual scores is measured by the standard deviation. Well, there is a standard deviation in a distribution of sample means as well. We just call that the standard error of the mean. We're going to talk about that in much more detail very soon. I just want you to understand that that is simply a measurement of variability between the sample means. Are you seeing how similar these distributions are? And in fact, we are going to be able to use that distribution of sample means to answer the same types of questions about probability. So, from this distribution of all possible sample means, we might ask ourselves, what's the probability of randomly selecting maybe 100 people and finding a sample mean, an average IQ of 110 or greater? Do you see how that's getting us really close to what we need to know? We need to know what's the probability of finding our sample data just by chance. When you have a population that has an average IQ of 100, it becomes very unlikely to measure a large group of people and find that that group has an average IQ of 110 or greater. That's exactly what we're going to need to know. How likely is it to find our sample data just due to chance, just due to sampling error? I mentioned that that parent population of individual scores gives birth to that distribution of sample means. But I still haven't really told you what is a distribution of sample means. Let's really dig down deep into that concept next. This page of notes will serve as a really good reference for you because it has lots of key information about the new concepts we're discussing today. For example, here's some key information about a distribution of sample means. What is a distribution of sample means? It is a distribution that shows all possible sample means taken from some parent population given some sample size. At this point, that might sound like Greek to you, so let's actually walk through an example. The only way I can show you how to do it without being here all day long is to use an example that's very, very small. So here is a population of individual scores. This is the population of X, individual X values. That is what I was referring to as the parent population. Just individual scores. Same thing we've been dealing with all semester long. You'll notice, though, that the population is very small. It's only a population of 4 scores. Let's not worry about what we're measuring. It's just a population of 4 scores. There's a 2, a 4, a 6, and an 8. So overall N, capital N, equals 4. And while we're looking at that small population, let's just go ahead and compute its mean real quickly. If there's a 2, a 4, a 6, and an 8, 2 and 4 equals 6, add another 6, that equals 12, add 8, that equals 20. So the sum of X equals 20. And 20 divided by 4 would equal 5. Go ahead and write that, like maybe right over here, just so we don't forget that mu equals 5. The mean of that parent population equals 5. From that small population of scores, I want to create a distribution of all possible sample means. For each of those samples, we need to determine its size. How many scores will be in each sample? In this example, let's use a sample size of 2. So small n equals 2. If I'm going to create a distribution of all possible sample means, what I need to do now is take every combination of 2 scores from that population of individual scores. So I'm going to take every single combination of 2 scores at a time. Once I find 2 scores from that population, I'll compute a sample mean, and then we'll list it in this table right here. You might recall that we learned about sampling with replacement, and I told you that lots of the things that we'll be doing for the remainder of the semester are based on sampling with replacement. Well, that's true with the distribution of sample means. So when we find every possible sample from this population, we will be using sampling with replacement. Let's go ahead and draw our first sample. Let's randomly select our first of 2 scores from this population. And let's just assume that I randomly select this score right here, a 2. So in this first sample, the first score that I selected is a 2. I'm using sampling with replacement, so now I'm going to throw that score back into the pile. And because we're creating samples with a size of 2, I now need to select a second score. And let's just say that just by chance, the second score that I select is that 2. So now my first sample has 2 scores, a 2 and a 2. So all that I want to do right now is compute a mean of those 2 scores. 2 plus 2 equals 4, that's the sum of X. Divide it by 2, which is N, and I get a mean of 2. This distribution of sample means that we're creating right now from that parent population is going to include every single combination of 2 scores at a time. So let's go ahead and draw 2 values for the second sample. Let's assume that for the first value that I select, I happen to randomly select this value of 2. So that's my first value for that second sample. We're using sampling with replacement, so I take that value and I throw it back into the pile. Now I need to randomly select a second value. Let's say this time I find the 4. So the second value in that sample of 2 values is a 4. Now I simply want to find the mean of those 2 values. So let's sum them up. 2 and 4 is 6. That's the sum of X. Let's divide by N so we can compute a mean. 6 divided by 2 equals 3. So there's my sample mean for that particular sample. in order to find a distribution of all possible sample means, we need to find every single combination of two scores taken from that parent population. So you can see for the third sample, I have a combination of these two scores, a 2 and a 6. For the fourth sample, I have a combination of a 2 and an 8. And in both cases, I computed means based on those two scores. The mean of 2 and 6 is 4. The mean of 2 and 8 is 5. And I'm going to continue to do that for every single combination. In this sample, we have the value of 4 and the value of 2. In this sample, the value of 4 and the value of 4. In this sample, the value of 4, the value of 6. You see where I'm going with this. Every single combination of two scores is listed here. And for each of those samples that consists of two scores, we compute a sample mean. So this list that you see right here contains all possible sample means that we could create from this distribution of individual scores based on a sample of two values taken at a time. When we refer to a distribution of sample means, all it means is we've taken all of these sample means that we've created and then we've graphed them. And you'll see that this graph right here reflects exactly these values right here. This graph shows one sample mean that equals 2. Here we see one sample mean that equals 2, and you see no others. You see two sample means that equal 3. There's one, there's the other, there are no others. You see three sample means that equal 4. There's 1, there's 2, there's 3. Four sample means that equal 5. There's 1, there's 2, there's 3, there's 4. So this is the data in graphical form. So this graph does indeed represent a distribution of all possible sample means. Well, that was a lot of work, and we wouldn't want to have to do that all the time for our data. And this was like the simplest example possible because it's based on a population of only 4 values and a very small sample size, 2. If we had to do this with real-world data where population sizes could be in the millions and samples could be in the thousands, it'd be impossible to do this by hand each time we needed a sampling distribution. Here's the good news. According to what we call central limit theorem, according to this mathematical principle, we already know how this distribution is going to look. So here's the key information. We don't need to create that distribution of sample mean from scratch. I already know its properties. I already know how it's going to look. Take a look at it. It's normally distributed. So we're going to be able to use the distribution of z-scores to compute probabilities. If I'm going to be using z-scores, I'm going to need to know the mean of that distribution, and I'm going to need to know a measurement of variability for that distribution. Here's the good news. I already know the mean for that distribution of sample means. Do you remember I told you that the mean for the distribution of all possible sample means is called the expected mean? You can just see it as the mean that we would expect to find. And I mentioned to you that the expected mean should be equal to the mean from the parent population. Do you remember we real quickly computed the mean of this parent population of 4 scores? And we found that the mean was equal to 5. What does the expected mean equal in our distribution of sample means? 5. So according to central limit theorem, I know that that distribution of sample means will be normally distributed, and I know that the expected mean, which is simply the mean of that distribution of sample means, will equal the mean from the parent population. Remember, parents and children, they tend to have similar characteristics. The parent population has a mean of 5. Its child, the distribution of sample means, also has a mean of 5. Well, look at these values. All of these sample means don't equal 5, and we can see that graphically as well. In other words, there's some variability between the sample means. Just by chance, when we're selecting data from this population, sometimes we will get means of 5, but because of sampling error, sometimes we'll get means of 8. Sometimes we'll find means of 6. These means of 6, means of 4, they're pretty common. They're likely to occur by chance. Do you see how we're getting so close to what we need to compute? How likely is it to find our sample data just by chance? Some of these means, like these means of 8, they are unlikely to be found just by chance. My friends, this is exciting. We're finding a relatively simple way to be able to compute probability based on our sample data. You might recall that in order to compute probability, we need some type of measurement of this variability that we were just talking about. Here's the good news. Remember, we measure variability in a distribution of sample means by computing what we call the standard error of the mean. The standard error of the mean is just a standard deviation of those sample means. So minimize it. In order to really understand it, just minimize it. The standard error of the mean is just a standard deviation. It's just measuring how much the sample means differ from that true population mean of 5 on average. So it's simply measuring on average how much do these sample means, look at all these different sample means. On average, how much do these sample means differ from that true population mean of 5? The good news is we've learned from central limit theorem that we can compute the standard error of the mean using this really simple formula. All we need to do is take sigma, which is the standard deviation from the parent population, and divide by the square root of the sample size. As I mentioned to you, parents and children tend to have similar characteristics. The variability that we see in this distribution of sample means is based at least partially on the variability that we see in the parent population, sigma. And it's also based on the sample size. In the next video, we will focus specifically on the standard error of the mean to make sure we know how to compute it and to make sure we know how to interpret it. But let's at least touch upon this specific point right now. It says, as n increases, standard error of the mean decreases. Once we think that out, that should make sense intuitively. Remember, the standard error of the mean is just a measurement of variability of these different sample means. That principle that we just looked at says that as n increases, as the sample sizes increase, standard error of the mean should decrease. What that means is, as these sample means are based on more and more data, in other words, as sample size increases, we have more and more data contributing to that group mean. As sample size increases, the standard error of the mean, the variability amongst all these sample means, should decrease. The reason that makes sense is because as sample size increases, we're coming closer and closer to measuring the entire population. And as we come closer to measuring the entire population, each one of these sample means becomes a better representative of the population mean. In other words, each one of those sample means comes closer to the true population mean. So ultimately, as we measure more and more people in a sample, we have less and less variability from one sample mean to the next. So as we measure more and more people, we have less sampling error in our data. And of course, that's what we want. We want as little error as possible in our data. So as a general principle, we want sample sizes to be as large as possible. Because when we have more data in our sample data is more accurate. And keep this in mind, for the past couple of weeks, we've been on the hunt for some way to measure sampling error. We just found it. Standard error of the mean is a measurement of sampling error because it's a measurement of variability from one sample mean to the next. It measures on average how much our sample data differs from the true population mean. Well, I think that's enough information for right now. Look, my friends, I know that's a lot of information to take in. I know you're going to have to look at this video more than once. I know you're probably going to have a question or two, and you'll want to make sure you ask me or a tutor. That's okay. You need to give yourself some slack. This isn't the type of thing that most people master based on their first viewing, but it is, nonetheless, something that we need to master. And let me mention this as well. Once we start learning a little bit more about it in the next video, you're going to see how we're going to put everything together. And as we put things together, everything that we're learning makes more sense. Just keep wrestling with these concepts. Keep learning more and more, and you're going to see it all starts to fall together. I'll see you in that next video. In the meantime, be safe.